Okay, here is the continuation of the exercise that we had last week, just for reminding you and bring you up to speed. We were about to set up and complete a flow simulation for an electronic box. This electronic box has given some information with that, which is the external temperature is given, heat transfer is given. This is something that we defined it when we setting up the simulation. We learned that different material has different set of the properties. Heat-sink aluminum inlet and outlet holes are thermally insulated, and capacitor is a copper fixed at the temperature. Power module, which is this big black box here, is epoxy resin fixed at 50 degrees C. PCB material, these green PCBs has a specific material, and you'll learn that the way that we did that, we defined a new material and assign it to these PCB parts. Electrical chips, which would be this uh, big chip, and as well as these 8 small chips, they have also a specific material that we also define it. And then also the fan was a POP ST412, and we learned how to define a fan instead of making a revolution. So just to review of what we've done, I'm gonna kind of go over some details, not gonna define it again, but I'm gonna review what we have learned. So if I right click here, going to general setting, it's gonna show me that in general setting, we defined a simulation based on a fluid flow and conduction. We skip radiation, it's not time dependent, there's no gravity, for example, is negligible, no rotation, because fan is defined with the different methods. And there is no free surface for doing that. This is an internal simulation. It already defined the leads to close every sealing point. Uh, so fluid that we selected was air, and all the solid, for example, I can, I can select a different stainless steel, or just for to make sure that I was selected aluminum 6061 for all the material that has not been assigned. Uh, what else it was? Maybe I just closed that too soon. Then for wall condition, we define that there should be a heat transfer coefficient that we define it. And actually, if you expand it, you see that it's a 5.5 watts for 10 degrees C, which that was the situation that is given here. And then for initial condition, we learned that it's a 14.7 psi at 10 degrees C is the initial temperature, and as well as all the initial solid temperature are at 10 degrees C. That was how we define it. And then for PCB, we apply that custom material. We learned it last time how to define a new material. You know, if I go to engineering database, you will see that in materials and in solid, there is some user defined that they can define for the material, and it's already assigned to these two material for the PCB and other component package. So we applied to that PCB, we applied it to all chips, 9 component, heat sinks made out of aluminum, all 3 capacitor copper, and this is epoxy resin. Something that it might is still doing that is this one. So just going everything, we define heatsink, we define capacitor and power modules, and we define these two PCBs. One thing that is left is the inlet and outlet holes are thermal insulated. So when we are putting the fan, you don't need to define it as thermal insulator because the fan would be here, but this part should be defined as an insulation. So we right click, define a solid, and then here it would be these 3 pieces, 3 leads that we selected here. Actually, if you wanted to delete like other leads, you can do that. So inlet holes and outlet hole, all 3 outlet holes. And you're going to predefined, go to It should be glass and glass and minerals, and you see that there is an insulator. So that make sure that this part is thermally insulated. Okay? Now we are done with defining the material and everything is being selected. So the only part that has not been defined is these light blue, which by default would be aluminum 60, which is our default component. Now boundary conditions. The only boundary condition that we have. Uh, so before that, maybe we have to go and take a look at how we define fan. Fan was something that we defined it, and the way that we define it, we learned that it's an external inlet fan. We installed it on this face, so that's the whole face that the fan would be. So this is the area that air would be flow inside. And if you look at the library of the fan, it's an axial fan, and if you go to POPST, it would be POPST 412 according to the information that is given, external inlet fan to define. And boundary condition we needed, so now this is inlet. All of these leads would be the boundary condition to open to the atmosphere. So right click and then you're selecting the inside faces of these leads, and then you are seeing that this is gonna open to the environment pressure, which environment pressure means 14.7 psi and 10 degrees centigrade. Okay, so we have the boundary condition. You don't need to define any inlet velocity or anything. You put a fan and take care of that. So let's define some goals. So if I'm going to global goals, and let's see what we can do. Let's say I will put the average dynamic pressure, average total pressure. So consider both the static and dynamic. Then temperature of fluid, I would like to know that what is the air temperature inside that I would like to see. Then let's put velocity, which would be for fluid velocity inside. It's important to know. What else? Not turbulence. Yeah, let's select average turbulent energy that we have here. What else we can have? So this likely temperature should be somewhere that we have to, okay, temperature of the solid that we have to select here. And then, yeah, probably that should be sufficient. And then let's put average. Oh yeah, we are selected temperature of fluid. Okay, good. That's it. Okay, we have enough of the goals. Then we can create mesh, which is essentially, if I define mesh, I can pick it at, it's a 3. I don't want it to have a very difficult and time consuming simulation. Okay, so let's go and run it. And it's a new result. Okay, mesh is defined. And if I go and see all the goals that we have, it shows how they are converging. I would pause the video and go back when the calculation is finished. Okay, so the simulation is finished now, and you will see that all of the goals have been converged at the end of the simulation. So it's all converged at the end of this. It took me quite a while to finish it, but it will finish. Now the simulation is finished, we have to answer for report the request information. First, we want airflow section view, which essentially we can create a section view of here and show the airflow. Maybe a cut plot should be sufficient for this purpose. Right click on cut plot, and insert the cut plot. Okay, take a while to doing that. Maybe it's selected front plane, which good. That's a good area. You know, essentially it's in the center, so we can create a good cut plot and you can see how the airflow is gonna go there. So maybe I can go with the even okay, say let's say put the airflow based on a velocity. So if I select velocity of the fluid here, and even I can select a vector, and those vectors also velocity. So it's going to show the direction of that, not only the value of the velocity, but also the direction of the velocity as well. Let's select, see what happens with that. And you see that these are small. You see that how these you have some high velocity here, right, at the fan. That fan is here with 4 meters per second. They have velocity here. I can increase the number of that to, you know, make sure it's much smoother. I'm not sure we can animate that, or we can play. Our play is gonna go up and down for the pipeline, but nothing else would be there. So, but how about we add more, maybe increase the size of these velocity vectors. So go back to definition and maybe, oh, that's a spacing. These are maximum arrow size. Yeah, let's make it, let's say 5 arrow size. The ratio is that. That makes a little more visible, but you will see that here there is not much of the velocity. Actually, velocity is close to 0. So sort of what we can see off of this is that's a good velocity here, but these PCBs might not get what we wanted. But we forget something in the beginning in this simulation, which is worth it. That's why I was wondering why the velocity is here, and that was the temperature of the component. So you have to essentially change something in the heat transfer and then redo the simulation. So I keep this cut plot because the simulation is not valid. Okay, going back, you will see that it says a few information that we need. Capacitor, all of them are fixed 40 degrees C. So in order to do that, let's unload that. Right click, unload, no value is that. Now we have to define some thermal loads. If you drop on the condition maybe, or source, yeah, source is the one that we have to define. So you have a surface source, but this is actually a volume source that we have. So if we define a volume source, and then we pick the 3 component, which would be 3 capacitor. And this capacitor, essentially, we can either define it heat dissipation, or you can define the heat transfer, like a volumetric heat generation, or you can say it's a fixed temperature, which this is what we wanted. And it says 40 degrees C. So we have to change this to 40 degrees C. So that would be the 3 heat source that we have. What other heat source that we have is essentially the power modules, which says the power module is fixed 50C. So with the same concept that we can. So we define it here, volumetric source, and that volumetric source, we have these power modules, constant temperature at 50C. This does not impact on the velocity of the fan that we see, but definitely it impact on the temperature. What other values we have is heat dissipation. So main chip is 5 watts, the small chips is 4 watts. So let's do the main chip first. That's again a volume source. So this big chip here has a 5 watts, and what's this? Oh, it's a 4 watts total. So essentially, it would be half a watt each. But we can go here to the volume, and we could say here's all the parts that we have. So each part essentially would be half a watt that we have here. Okay, okay. So now we have all the heat transfer out of the main chip, small chip, and everything. Now we can run the simulation with the new calculation. Mesh would be the same. We are not changing. I will run it again, and again I would pause the progress of the goals until the model gets converged, and I can get back to you. Okay, again, these solvers converged. Um, Going back to see our, I will show the plot that we have. And as you see, it's nothing has changed. Now, the second one that it wanted is air temperature section view. So we can change the section view that we have right here from velocity to go to temperature of the fluid. Okay, and essentially this shows the temperature. So velocity would be the same, these vectors, but the color would change to temperature. And you see that the initial temperature, which is blue, is 10 degrees C, which matches the outside temperature that this everything is located. But as air travels, it's get heated up more. But you will see that like in the back, it's a very hot spot here. It means that the cooling is not that good because air cannot reach up to this side to cool that off, and eventually it's gonna get out of these open into the atmosphere. So this is first two, and then we wanted to see the airflow trajectory. So I'll just hide this one for a second. Go to flow trajectory, insert one. Let's select this face to generate, say, with 80 for starter arrows. And what I would like to see maybe it's velocity, just show that how fast air gets into this. We can change later to another that we have. Maybe can a little more in them because the arrows are very small. Uh, let's say I'll pick 150 and make the arrow size like better. Let's do the animation and see. So you will see that kind of how the air is gonna go there. You will see that how this front face of the heatsink essentially send this one back. Uh, you'll see that how the air is trapped here, sort of like a vortex formed here. Definitely is not that good here. You see that the velocity how is small, like almost zero. Actually, maybe we can change it to the temperature fluid, and you will see that how the fluid is. You see that it's cold with a 10 degrees C, but here it's approximately 20 C, and see how it's going to get hot. This is going to sort of showing that if you want to see other sort of like a presentation, you can, for example, let's the arrow go to the pipe to see how this is moving. And the good thing about pipe is it's going to show how initially it's a start. It's maybe not that great. I think arrow was probably. Anyway, we'll hide this one. So now that we move forward, now let's calculate a few things like average temperature of the main chip and the small chip. You know that how hot is this main chip So remember that main chip has 5 1. So maybe for this one, it would be like a volumetric would be better because we wanted to make an average across a volume. So let's insert a volume parameter. I will select main chip here. And I want to know what is the solid temperature. So if you put there, it's going to show you, I think I will show it. Shows that the average temperature is 32 degrees C. Now, you can define another volumetric, which would be what is the average temperature of all of these small chips. You can do one at a time, select all of them, and then if I want to know that how much is the average temperature, it will show you which essentially says 20 degrees is the 23.49 is that. Show that how it's gonna go. So see that the main chip is much hotter, but because the dissipation was higher as well. So 5 degrees or the half of what that's why, even though that is this gets cooled very well because it's right in front of the fan. But this is not getting that cool, but they are not generating that much heat. Okay, go back. It says what is average fan static pressure that you have. So uh, so we can, for static pressure, we can get a surface parameter. So we're going here and create a surface over here that fan is here. And I want to know that how much is the static pressure. So if I go here, show, it's going to show me that this is 14.7 is the average static pressure that we have. And then if I want to know average outlet air mass flow rate, so that would be across these. So maybe we can define another surface parameter, and for that I will select all these three faces that we have, and air mass flow rate. So there's mass flow rate. Yeah, mass flow rate. That's the name. And we show that the average mass flow rate for this is negative because it exits out of this. It is a 32 kilogram per second. Um, so you can, for example, here, I go there, maybe if I go to options, it's going to export it. I was wondering if we can change the unit, but essentially with the energy, that's what it's kilogram per second. Could change it to like a more IPS unit if you want. And one thing that I would like to show is if I can, one of the important thing probably is about creating a flux plot. This is something that is very important in thermal analysis that shows how heat transfer between the components, how much heat we are getting from outside air, and each how much is the share of each component. If I right click and insert a flux plot, and here you can select like every part that you have. If you say use all components, let's see what happens. So if I use all the components that I have, it's gonna create a sort of massive diagram that we have. But let's see if I can, if I see how we can sort of put like something to be able to read that. Is that we have so many things. Not a little bit, but how can I move it around? Middle click. So this is show how each component is gonna generate. So you see that the ambient temperature, how much water it receives. Sort of my display is finicky, but uh, it shows that how much each component receive, like dissipate or receive the heat from outside. But like if you see that, for example, ambient, the total ambient is gonna uh, absorb 17.79 watt above the entire other generation. But like this subdomain is the air. So you see that, for example, heatsink, how much is that? Heatsink is receiving 3.805, which that's the amount of the air, the amount that goes in. And then opening, like how much opening is going to go out. Like ambient is receiving that much air, and opening is putting 36 watt to the entire, it's going to go out. It's pretty much a big deal of that. So this is going to show us how much each component, you can relocate it to show that, or you can, for example, remove a lot of these, like a capacitor. If you don't want it to put some parts, you can easily generate a small to create a like a much easier sort of flux block. For example, you can select, but that's gonna give us a big overview of how much heat is gonna exchange between different components in this flux block. I hope you enjoyed from this information. Thank you.